flexibility.
Hi, Supratim.
Hi, Shilpa.
So, let us start the webinar today.
Great.
And yeah, hello guys, welcome. Good afternoon, everyone. Welcome to our webinar on advanced safety solutions for tuggers. And I'm your host, Shilpa Parimi. I am the lead technical writer at Ati Motors. I work closely with our engineering and product teams to document and communicate the technologies powering our autonomous solutions. It's pleasure to be your moderator for today's session. A brief introduction on Ati Motors. We are Bangalore-based robotic company specialized in the design and manufacturing of autonomous and electrical vehicles for industrial material movement. Our flagship product line are the Sherpa series. It includes a range of autonomous mobile robots, famously called AMRs. From mechanical design to AI-driven nav systems, we build our systems in-house. Our Sherpas are designed to integrate seamlessly into existing workflows, improving productivity with zero infrastructure changes using natural navigation technology. Coming to the context of the webinar series, this webinar is a part of ongoing knowledge sharing series, which we highlight innovation in robotics and automation for industrial environments. Through these sessions, we are aiming to bring forward expert insights, real world applications, and thoughtful discussions for the future on the future of autonomy. And today's topic is advanced safety solutions for tuggers, which focuses on how AMR tugging solutions can boost safety, efficiency, and automation across industries such as automotive, FMCG, and all. We will look at real world case studies from our leading manufacturers and share actionable insights that reflect both engineering challenges and on ground learnings. Our key speaker today will be Suprotim. Suprotim serves as principal autonomy engineer in Ati Motors, where he leads initiatives in controls, navigation, and perception systems for our autonomous vehicles. With extensive experience in developing advanced robotic systems, he has played a very key, pivotal role in evolving the Sherpa series in Ati Motors. I think from bot 0 to bot 140, he is our principal engineer. And Suprotim's expertise centers on seamlessly blending cutting edge algorithms with real world engineering to deliver reliable and robust autonomous solutions. His practical system level perspective and knowledge will help us and anyone today to understand what are the problems that we face on safety with tuggers, and he will be presenting the real time challenges which we have faced, and then he will be explaining you how we have overcome it and how anyone can overcome it. uh,
Thank
I would, yeah,
yeah.
I
Thank you
would
so
like a
much for the
little,
introduction.
excuse me, Subratim.
Thank you so much for the colorful introduction.
Yeah, that you are, you have to agree upon that, that you are. Okay, so one more thing I want to tell our participants today is that this will be a 40-minute session with 10 plus minutes of question and answers. So you, anytime you have a question, please feel free to post it in the question and answer feature. This session is being recorded, and this recording will also be shared with all the registrants after the event. Supratim, let me just introduce about our fleet of tuggers, and then I'll hand it over to you.
Yeah.
Yes, guys, these are our Sherpa Tugger lineup. This is the Tugger family we have. Most importantly, can you hover over XT light, Supratim?
Uh,
Yes.
Let me get over here. Yeah. So here is
Yeah. No, no,
XT.
XT Lite. XT Lite is the proven workhorse for us. We already have this deployed in 27 unique shop floors across India and in various sites. Plus, we have other Sherpa series also deployed in all these places. This is already a proven workhorse for us, and its carrying capacity is 1.5 ton, and it has the sensor stack which we have already spoken in our previous webinars. Krishna sir have already spoken about the internal and external sensors and how each sensor work and why we chose this stack of sensors for our Sherpas. Introducing Sherpa Pivot. Pivot is our mini tugger, which can help us with the payload of 500 kgs. And Sherpa XT. Can you hover over XT, Suprotem, once? This is going to be, yes,
Yeah.
this tugger will be able to carry payloads more than 1.5 ton. To be precise, in Indian kg terms, it's 1500 kg and greater loads it can carry. Now, with the introduction to our Taga family, now I give the hand over to Supratim. Supratim, please take over.
All right. Yeah, thank you for all joining this afternoon. Going to try and keep it within about 35-40 minutes. And just so that everyone is familiar with the terminology that we will use throughout the webinar, I will do a quick 101, including some of the topics that we spoke about last time. So as Shilpa mentioned in the last slide, we have a variety of tuggers available in our lineup. And well, they all run on a whole bunch of sensors. There's a 3D LiDAR, which is the main sensor that we use for our autonomous driving. But we also have other additional sensors that help clear some of the blind spots that we have, or to perceive obstacles and other things in the blind spots that we have. So we have a RGBD camera, so that's color plus depth. We have other safety sensors around the body of the robots, like ultrasonic sensors. These are sensors that are available in most cars these days. And we have other low-lying sensors like 2D lidars, which can be placed underneath the robot or around the periphery of the robot, which can perceive low-lying obstacles. Right, so you can see the field of view, the FOV of the various sensors in figure 1. You can see the LiDAR placed atop the robot, and you have the camera along with ultrasound sensors covering up some of the blind spots that are shown in figure 2. You can see that there is a large circle around the vehicle, and at ground level, that is the blind spot which we are covering with these additional sensors. Right? And just a brief on autonomy itself. Basically, for any autonomous robot to go about its business in any environment or a factory or a warehouse, we need to answer 3 very fundamental questions, which are: where are we? What is around us? And what do we do next? Where do we go? How do we get there? Etc. Right? So to answer the first question, we need to know where we are in that particular environment. So with the set of sensors that we have, the 3D LiDAR primarily, we build a map of the environment. And as we move through the environment, we localize, which basically means we take a scan of the environment and match it against the map that we have created. And with some fair amount of accuracy, we know where we are. Then, of course, we need to move. And before we move, we need to know what's around us. Is it safe for us to move? How much space do I have to move? And what other obstacles do I have to deal with when I move? So you can see in the second column of plots, you can see the camera view of one of the robots. It is able to see some pillars. You can see the ceiling. You can see another robot to the right-hand side of the robot. And that is in RGB, and you also get a depth version of that as well, which you can see in the plot below, which is basically what we use to perceive these obstacles. And of course, along with the camera, you have a nice 3D view around the robot itself. And now the third thing is we know where we are, we know what's around us. Now we need to execute a mission or a task. So the Sherpa or the robot needs to move from station to station. So now it needs to plan. So it needs to know what route to follow, and it needs to know how to follow that route. Environmental conditions change, the payload of the vehicles change. It needs to figure out how to move the motors, rotate the motors, steer around obstacles, and achieve its task. Right? So any questions about the sensors and autonomy in general?
Supratim, I am getting some very generic questions, but these questions were already answered in the previous,
Sure. We can go over it very briefly.
So it's like, how do cutting edge technologies like sensors and automation enhance safety for tugger operations and pedestrians in busy facilities? I think going ahead they'll get this answer, but if you want to give a little answer for
Yeah.
this.
Yeah. I mean, observability is key, right? So you can only be as safe as what you can perceive. So adding sensors, running cutting edge algorithms on the data collected from these sensors will allow you to perceive the environment better. And that is how you will guarantee safety and reliability.
Yeah. So Then there is another question, but too deep. What best practices should organization adopt to ensure ongoing compliance with evolving safety regulations for tuggers?
Yeah, well, yeah, at some point in time, you kind of have to meet in the middle. Robots can provide a solution to a certain extent with, the sensors and the algorithms that we run with, but it also helps to have standard practices, at least safety practices, discipline around the manufacturing area, discipline around the lanes where the robots are flying. That goes a long way. So there are basic, standards, industrial standards that what can follow, and there's a lot of infrastructure that can also be done, keeping AMRs in mind. A lot of factories, that are 50, 100 years old even, were designed around people being the main material movers. In 2025, that's not the case. Factories are going to get more adoption of robots. We can, design factories in such a way that they are more amenable to, hundreds of robots running around and getting the job done.
Okay. And in this path planning and control kind of pictures here, we
Yeah.
do have a bot. Okay.
Mhm.
And all the blue things are, what can you explain just that once
Sure.
again?
Yeah. Yeah.
Yeah.
So if you can look at the path planning and control plots, the robot is in pink. So that's the pink color box that you see in the center of the two plots. The
Okay.
grayish color line, the dotted line, around the dotted line rather, is the path that the vehicle needs to follow to execute its mission.
Okay.
Um, and you will see that there are red color patches.
Okay.
That is basically the LiDAR point cloud data. Of course, it is projected into a 2D plane. The LiDAR
Okay.
is a 3D sensor. It perceives everything in 3D, as you can see in the first figure. But we kind of project
Yeah.
it 2D plane so that it's just easier to process. And we do the path planning on that. So anything that is red is basically points that you have perceived above ground. The blue points that you were mentioning, Shilpa, are the ground points that we have segmented from the point cloud data, and green is basically stuff that we have not seen. So we are kind of uncertain about it. So we don't
Okay.
want to go near the green. But as we keep moving, you will learn more about the environment, and you will start populating the region around the robot, and you will know what is safe, what is drivable, and what is not drivable.
Okay. Okay, Spratim, that's it. You can go to the next slide.
All right. Cool. So yeah, just wanted to show whatever we talked about in action. You can see the beams of the LiDAR. This is, I think, a 32 beam ouster LiDAR. So as the robot moves, it localizes. It's in this warehouse environment. It's able to perceive all the stacks, the trolley behind it. You can, if you can notice very closely, you can even see some vehicle dynamics at play. This is the Isaac Sim simulation environment developed by NVIDIA. So you can see the wheel of the trolley rotate around. So you're getting real world physics as well simulated. So this is a great tool that we use to develop our software stack. Um, and yeah, you can see the vehicle moving around doing its thing. All right, so now to the heart of the matter. Um, Tuggers. So what's so special about Tuggers? Well, tuggers, as the name suggests, tug trolleys, and trolleys are tough. They provide a whole bunch of challenges. There is a wide variety of trolley form factors that robots have to deal with across environments, factories, and warehouses. They come in multiple configurations. Um, of quite often, and you can see in these plots below that there are multiple trolleys attached, and the more trolleys that you attach, you will face certain challenges. We'll go over those as we progress through the slides. Trolleys are pulling, I mean, you're pulling a trolley which can, as Shilpa mentioned in the first couple of slides about the vehicle payloads, they can be up to 1.5 tons or 2 tons even. So payload matters, the conditions of the trolley wheels, the trolley chassis matters. So these are all challenges that we have faced over the years at Ati, and we're going to look at some solutions that are in the works that we are looking to use to solve some of these challenges. So just a quick fun question for the audience. If you look at figure 2, can anyone guess how many trolleys are actually attached to the vehicle? You can see the vehicle in pink, and there's a whole bunch of these cart-like entities that are following the vehicle. Can anyone take a wild guess as to how many trolleys are being pulled?
Please put your answer in the chat section so we can understand uh, your participation, guys. If no one are understood or can't see or
Yeah,
what it
please
is.
feel free to stop me at any time and can ask me any questions, especially about these plots.
But to
So
me, it looks like they are series on both sides, and one, two, three. I can understand till three because the tracing line is very this. So you can, I think, give the answer, Supradev.
yeah, okay. So anyway, in figure 1, just for everyone's clarity, the vehicle is in red and it's pulling 3 trolleys. It's taking this S-shaped curve, and you can see the paths that the trolleys themselves take are quite different from each other. So that itself is quite a challenge. But 3 seems quite trivial compared to the 12 trolleys that we are pulling in figure 2. So this is 2 rows of 6 trolleys, so a total of 12 trolleys. And you can see, especially while turning, they are taking yeah, quite a wild trajectory around the corner. And that obviously is quite a challenge. And as you can see here, the LiDAR is able to see the first couple of trolleys fairly distinctly. But as you approach trolley 11, 12, I mean, even yeah, the third row of trolleys onwards, it's very sparse. The set of points are very sparse. So it's difficult to see the trolleys. So these are, yeah, some of the challenges that we have seen over the years. So as I mentioned in the last slide, it's difficult to even see the trolleys. And the reason we need to see the trolleys is because once you know where the trolley's position is, that's when you can start to apply some of our safety algorithms, etc. So the first step is always detection. Where is the trolley? So the trolley is, I mean, it's obviously going to be attached to the vehicle via a hitch. So one technique that we had used to detect the trolley is to use the lidar. At least for the first trolley, it is quite crisp, as we had seen in the previous slide. So we have a set of lidar points behind the vehicle. You can see in figure 1. You can see this U-shaped uh, surface of the trolley that the lidar sees, and then we do a scan match against the mask of the trolley. We know the dimensions of the trolley beforehand, and then we know the pose. The
No,
position.
can you hover? I'm sorry to interrupt. Can you hover over the U-shaped thing you are pointing it at?
Yeah, so you can see here there is this set of
Okay.
points that the lidar sees.
Yes, okay.
So that is kind of like a signature of the trolley. And now what we need to
Okay.
do is we need to keep searching for this signature. That's how you know what the pose of the trolley is. And as I had mentioned, the trolley is rigidly linked to the hitch. So all you really need to detect or measure is the angle that the trolley is making with the vehicle, right? Because the trolley is rigid. It's never going to change in length or width. So
Okay.
we're trying to scan against a search space of masks, and finally we see which position we get the most hit lidar point hits, basically. And that's what you see in figure 3. As the vehicle is moving through the factory, the first trolley at least is quite clear. And where you can
Yeah.
see a bounding box drawn around the first trolley. So that is our output of this algorithm. So we have determined the position or the pose of the trolley. And now you can see the first trolley is quite crisp, but as you go through the corners, you can see here, we are losing a lot of data from the second and third trolley. That is
Yeah.
occlusion from the first trolley, occlusion from the corners or pillars that we are going around. So here you can see we are barely able to see anything, especially when the vehicle is straightened out. The first trolley kind of blocks out any view of the second, third, and fourth trolleys, etc. So these are some of the challenges. But for the first trolley, at least, it does a fairly good job,
Okay.
right?
So going ahead, we have solutions for all these challenges.
Yeah, we're actively working on quite a few solutions for this,
Okay.
which I will move on to the next slide for. So another approach, of course, is to use AI. In this case, we are using a neural net called Point Pillar, which is it's better able it's able to basically filter out noise a lot better, and it is able to classify these trolleys a lot better than a simple scan match could. Because for the scan match, I need to know some certain details about the trolley mask. I need to know the length and width, the signature of the trolley. Here it is a little more generalized. That is the beauty of AI and ML. So here you can see that it not only does a great job of detecting the trolley, but you can see over here that it is also able to classify the person as well, the human. So it is able to do human detection as well. So now the benefit of that is we can change the behavior of the vehicle, or we can adapt the safety layer of the vehicle to be more cautious if there is a human seen near the trolley.
So all these red marks are not just obstacles, but it can also detect that which is human and which is
Yeah,
just an
yeah. So
obstacle.
whereas in the last slide, all you see are a bunch of lidar points. Here you are getting a nice bounding box of the objects that you have been able to classify, basically. So you
Yeah,
can classify a trolley versus a vehicle versus a cart versus a human. That gives you a lot more information. It gives you semantic information. So now you know not only that there is a bunch of obstacles there, you know what that obstacle is. And that allows us more freedom to apply other techniques to be safer and to be more efficient in terms of our path planning.
that's wonderful. Okay.
Right. So I'll just show you a top view and a side view of the same. You can see that there is a convolutional neural net that we use. That is the backbone of point pillar net. And yeah, it just takes in point cloud data from the LiDAR, and it spits out whatever it has classified. So trolleys, carts, humans, etc. So you
Okay.
can see here that the person has come between the vehicle and the trolley, and the vehicle immediately stops.
Yes.
Yeah. And then once the person is gone, it goes about its business again.
Okay.
All right. And so now that we have looked at trolley detection, what do we do with that? We have to do something, right? So first and foremost, if you do see that there is an obstacle that the trolley is expected to hit, you probably want to take the safest bet and stop. So if you look at figure one, you can see again in pink, the vehicle is moving along a certain path. And behind it is a much wider trolley that is in the yellow boxes that you see. And you can see a big black color circle. That is an obstacle that we have detected. Now, if you look closely, the vehicle itself does not seem to be colliding with the obstacle, but the trolley is. So,
Right.
so that is the added layer of safety that you have when you detect your trolleys. You can be confident about what not only what the vehicle is going to hit or expected to hit, but you can also account for the trolley. And with that knowledge, you can extend it further. You not only do you want to come to a halt when you see an obstacle, but you may also be able to traverse around it. So you can see in figure number 2 that the vehicle is able to move around the obstacle that it had seen. So it has a bunch of candidate paths in red, you can see there, and it is always looking for a collision. If it happens to find a collision, it will take another optimal path from that set of paths that will take it away from the obstacle that it has seen. And it will rejoin the path once it is clear to do so. So now with the
Yes.
added knowledge of the trolley's position, you can account for the trolley for this avoidance maneuver as well.
Okay. Yeah, it's quite clear. There is a
Yeah.
path, and
Yes. Yeah.
yeah, in the this so it went out of the path, and then it has self-corrected itself
Yeah.
after a
Yeah.
certain point
Yes.
of time,
Yeah. So you can see the
because it
path is
knows. That
Uh,
all the trolleys have crossed that trajectory and then it has
yes.
corrected into
So
the
it's a
right path.
straight line path. It is just going north to south and back. And
Okay.
there is some box kept right now to its left-hand side. So it
Okay.
just detected that and it was able to find a feasible path around it, a safe, obstacle, collision-free path around it.
Okay.
Right.
Yeah.
And you will see the same here. So basically, there is, like I said, there was a straight line path that was predetermined for the vehicle to follow. But as and when it sees an obstacle, it has a bunch of paths that it basically optimizes over in terms of obstacle distance and of course kinematic feasibility, and it chooses the optimal path to get around the obstacle. And when it is free, as you can see in the video below, it rejoins the path. So here you can see that it is tugging a fairly largish trolley and gets back only when the trolley is safe around the obstacle. So it goes
Yeah.
on for a few meters and then rejoins the path back.
Right. This picture is more clearer than the. I mean, it added the more clarity to the previous slide.
Yeah.
Yeah.
Yeah. I think the previous slide didn't have a trolley, and this one has a nice distinct trolley that you can see.
Truly correct.
Yeah.
Yeah.
All right. So here's yeah, our testing facility in Bangalore, along with a visual representation on the side. You can see the trolley is much wider than the vehicle, but the vehicle is accounting for the trolley and making its way safely around the blue color box that has been placed in the path.
Yes. So good.
Right. So, any questions about obstacle avoidance and trolley
Yes.
detection?
Yeah, I do have some here. It's like if something comes between the trolleys, then what is the safety precaution for the same? I think we just saw the video how a guy have come in between two of those. I mean the trolley and okay, here this guy is asking between the trolleys.
Yeah, yeah. So
All right.
if you are able to detect the trolleys, let's say you have three trolleys and you know exactly where the three trolleys are. Let us say the lidar is able to see all three trolleys. Then you know what the trolley's bounding box or the mask is. And any point seen between those masks, provided of course that the lidar or any of the other sensors see it, it will be able to stop,
Yeah.
right? But in the case that for whatever reason, let's say the trolley is opaque, or the first trolley is opaque and it's quite big, the lidar may not be able to see around it, right? So in that case, you probably need to add additional sensors either on the robot, or as I will show you in this slide, you may want to instrument sensors outside of the robot, perhaps at critical intersections where you expect multiple robots or a lot of footfall in terms of human beings in the environment. So here you can see, we call this Ati I. This is our latest uh,
Yeah, so we have worked on some of these sensors, which are not only the internal part and on robot, but we do have ATI and several other plugins, which would
yeah.
actually help in detecting between trolleys, behind the trolleys, etc. Yes.
Yeah, so here you can see, I'll play the video again. You can see
Yeah.
that the camera is placed atop the wall at this critical intersection. And the camera detected a foreign robot in this particular case approaching the intersection. Now, of course, you don't want to risk the foreign robot hitting the vehicle or the trolley, especially if you have minimal observability around the trolleys. So you could rely on the AI to tell you that there is another robot, let it pass. It's kind of like a virtual traffic signal. And once it is safe to do so, you can proceed with the trip, right?
Yeah. Then we have one more question. How can data driven insights from advanced safety systems improve operational efficiency while reducing accident rates?
Yeah, so I mean, accident rates, of course, the trolley detection kind of speaks for itself. Not only do you want to account for collisions with the robot, but you want to make sure that the trolleys don't sideswipe boxes. These could be, critical payload either on the trolley or lying around in the facility. You don't want to damage any goods, of course. And obviously safety first when it comes to humans who are operating in these factories. You don't want to get close to sideswiping anybody. So obviously this suite works, but with the added benefit of obstacle avoidance with trolleys, you can also maneuver around them safely, and that will improve your tact time of the robot's missions and the material movement as well.
Yeah, and so we do take all these readings, we analyze here, and we try to find out solutions. If we already have how to correct it, if not, we also try to get new solutions for it because we have our Supratim there, right? Okay, we have one more question too. I mean, we have few questions.
Sure.
You want to take it now? It's okay,
Yeah, yeah,
right?
we can take some right now. It's kind of like half time.
Have them, yeah. So this is like the same question when in between the trolleys and behind the trolleys, the answer is same. It's Ati intelligence. Yet I'll read out the question. When a man stands behind the robot on the edge of the trolley, will the robot start or not? So it's like
Yeah,
restarting once it
yeah,
restarts.
as you
Yeah.
can see, it really depends on the fidelity of, at least if you look at the point pillar solution, it is pretty good at classifying the trolley apart from the human, right? So
Okay.
even you saw in the video, maybe I can just go back. Uh, the human does come pretty close to the trolley, so he's almost at the edge of the trolley, and it is still able to classify pretty well. So in fact, the person is interacting with the trolley by the looks of things. So this is able to do a pretty good job. And again, if you have a pretty good estimate of your trolley mask, you will be able to distinguish. And we are also running, as I mentioned here, we're running a lot of filtering techniques. We're running a Kalman filter here, so that will be able to make sure that you are not too sensitive to noise around the trolley.
Yeah. Now, one more question. How do you balance the cost of safety technology with the long term value it brings to your organization?
Yeah. So cost is usually not something that I deal with too often. I really, yeah, I always am in favor of the nicer, more expensive sensors.
And
The
safety first,
yeah,
whatever
safety
can,
first, yeah, obviously.
make
But
sure that
no, I
we are
think
doing.
in today's day and age, these sensors are only getting cheaper and cheaper. So now we can afford to have a gamut of sensors on the robot, which you may not have been able to do 10 years ago, let's say.
Yeah, but then we are always using the futuristic, sensors like 3D lidars when most of the
Yeah.
people are still using the 2D
And it
lidars and
is,
all that.
yeah, and it is not only the case that sensors are getting better, but algorithms are getting better as well. So you're able to do more with cheaper sensors now than you were able to do before. Like for example, the ITI just uses an RGB. It doesn't need anything more than something like a simple webcam. This is some 480p or something like that, and it does a pretty good job at detecting the foreign robot.
Okay, then I do have three more questions. A couple of questions from Mukunda here.
Yeah,
So, when you mention industrial safety regulations, do they also include software safety guarantees?
yeah,
Just for comparison, automotive sector uses standards like AutoSir that put specific constraints on the entire software chain from sensor processing to
right, right,
interface to call a system safe.
right.
Are these specific software safety requirements to be met to be considered deployment safe in warehouses? That's the
Yeah, so
question.
AMRs also have their bunch of certifications. I mean, there is a CE certification standard, ISO standards for AMRs. For example, sensor redundancy. So, for example, for encoders, they suggest or the certification mandates that you have additional safety sensors in case that one of the encoders conk out as a redundancy. And they also have standards in terms of braking distance for when you perceive obstacles. They need the vehicle to be within a meter or so of any obstacle that it has perceived. So yes, there is a set of standards that are being followed. I think there was a very recent update perhaps a 2024 or so update to these
And
standards.
then we are getting them certified too. Yes, it is actually.
Yeah, yeah.
And the second question from the same guy is, when using AI based interference to make safety related decisions, how do you guarantee determinism and explainability to
Yeah, that's
these
a great
models?
question. Yeah, and then that's something that you always have to take with a pinch of salt when it comes to neural nets and AI. But that is where the other sensors really do, and not just other sensors, other techniques do come into play. Although the AI may say that it is safe, the other sensors are still running to make sure that you are never going to collide. So those are more classical techniques which are deterministic, right? So the AI is giving you some sort of hints, at least in terms of semantics, but your sensors are still running in terms of what you see is what you get. So it will never make a faux pas in that regard.
Yes. And then we have question from Kartikeya asking, what's the max speed and the reaction time to stop the tugger?
Yeah, so the max speed of these tuggers, as we saw in slide one, was 1.5 meters per second. And basically, and I mean, this is how humans drive, right? As you go faster, you tend to, in your mind at least, have a larger braking distance or a larger safety padding or a more dynamic safety padding. I mean, there are concepts in robotics like time to collision and stuff like that. So the faster you go, the more cautious you probably want to be. And as you get into more constricted, narrower environments, you may relax your safety constraints, but at the same time, you also go slower. So it is a dynamic process in terms of detecting these collisions and stopping. And I mean, as soon as you see an obstacle, you start slowing down gracefully. You want to avoid jerks, of course, but you make sure that you are never colliding with an obstacle.
Yes, for now, those are the questions. And
Okay.
guys, you're always welcome. Please get in touch with Ati Motors, visit our website, and write inquiries and ask more questions. Our team will reply to you. Let's go ahead, Supratim.
Sure. Okay. So we covered trolley safety in the past couple of topics. Now we're going to look at something that is something a little more fun. So here what we're trying to do is the vehicle again is in pink and there is an orangish color, smaller trolley attached behind the vehicle. But one thing that you will notice is that the vehicle is not moving forward, but it is moving backward, trying to park the trolley into a parking bay. So now, of course, this requires trolley detection. It also requires obstacle detection around the trolley because you don't want to park into something that is already there. So, but you're also using the trolley's position that you've estimated to plan a feasible path into the parking bay. So this is a path planning problem, basically. Right, so this will definitely add value to a lot of folks in perhaps warehousing or manufacturing, where you may want to cover this last mile of getting the goods from the trolley into let's say a packaging or into the conveyor line. Here, the vehicle itself can drop it into wherever you consume the material on the trolley, auto unhitch the trolley and move on to the next trolley. Right, so you could potentially see hundreds of trolleys being picked up and dropped at the final destination with this algorithm, right? And I mean, we spoke a lot about preventing collisions, but I mean, bad things happen. That's, the nature of reality. We want to make sure that we do not aggravate anything that we may happen to hit or something that happens to fall onto the vehicle or to the trolley. So this is an impact detection algorithm. So this is where a couple more sensors come into play. So you have the IMU that detects a spike in the vehicle's movement. And there's also current sensor that we use to gauge a spike in current due to the extra load of the impact. And the vehicle will detect these anomalies and it will stop. It will make sure that it does not aggravate this impact at all. Yeah.
So we are working on it already. Since this is a slow mo video, I think the it looks like there is a latency, but then the vehicle stops immediately, doesn't it?
Yeah. This is in
Bec-
real time. But
Yeah.
you can see that there is a fairly large spike in current compared to the normal operating currents in the vehicle, and we stop. We want to make sure that in the odd chance, and that's a very small chance, that something does collide into us, we do not proceed any further. It's always safety first.
Okay.
So yeah, so these were some of the challenges that we face. When you load the trolley dynamics do come into play. The heavier you get, the faster you get, the more you see that the trolley is becoming a factor in terms of the vehicle's performance. And we also saw that you are often bound by the observability of the sensors around the vehicle and around the trolley. And these change from site to site or factory to factory. There are a lot of dynamic environments where there's a lot of clutter, there's a lot of vehicles or human beings that are working. The trolleys themselves may be very different. The trolleys may degrade over time. So the wheels of the trolleys may pick up loose material and become stuck. The trolley chassis may be lopsided, and the weight distribution becomes imbalanced. And in a lot of these cases, you do want to throw in some extra sensors in the addition to the 2D to the 3D lidar camera and IMU, etc. So yeah. And yeah, some interesting solutions that we are thinking about right now at ATI are things like how to use learning-based approaches for some of these problems. So this is a very interesting algorithm. Let me mute it. Uh, by folks at I think UC Berkeley, maybe 7 or 8 years ago, where it is learning about the vehicle dynamics as it goes. So initially, you can see that the time it takes to execute this path is about 11 seconds. And as it goes along, it is learning about the vehicle's dynamics. It's learning about the optimal path that it needs to take, and it is able to go faster. So it is learning on the go basically, and we think that we can do the same with trolleys perhaps. We can learn that the trolleys have degraded. We can even say that, hey, the trolleys are degraded. Maybe you want to do a maintenance, or the vehicle motor has degraded and you want to do maintenance. You can learn about the varying environmental conditions that you may be facing on a day-to-day basis, and you can optimize speed according to that, right? So now you can see that the vehicle is completing the same route in about 6 seconds. So it's halved its lap time. So yeah, pretty cool stuff.
So generally, we also test with all these kind of simulations by giving different kinds of scenarios. By with one trolley, two trolley, different payloads. Do we do that in our testing phases, Pratik?
Yeah. We do try to test with whatever trolleys we do have, but it pales in comparison to the amount of trolleys that you would face when you are, at a customer site. I mean, you have hundreds of trolleys all across.
But
So
then our support engineer goes there and we test whatever use cases they give and we try to find a
Yeah. So we
solution
try
for that.
to make sure that we are customizing based on the trolleys. We optimize the paths, the safety constraints, etc., based on the trolleys that we are pulling.
And all this insights we get because of our data.
Yeah. It's
Yeah,
always backed up
wonderful.
by data.
Wonderful. Yeah. Please
All
go
right.
ahead.
Yeah. So yeah, so we had initially looked at a trolley parking problem, but this is a little more dynamic in the sense that the path that we had given earlier in the earlier instance, a few slides back, was a predetermined path. But here you kind of want the vehicle to figure out how to park on its own. So let me just play this a little faster. So here you can see there's a small vehicle that is trying to park a very large, long trolley into this narrow parking bay. So it has started off in the right-hand side of this lane, and it is able to park. Now let's say, things have changed and it needs to approach from a different angle or a different position. It will adapt around the environment that it sees. So it figures out a path based on the environment and the conditions, the space around it, basically. So you'll see here that it is able to take it's able to figure out a sharper path to park the trolley into the bay. And I think the next example is even more outlandish. Now it is approaching from the eastern side of this lane, and it is now going to do a 3-point turn, but it has figured it out on its own. So this is a search-based planner. So it basically searches based on some motion primitives around the space available, and it figures out the path that the vehicle and the trolley need to take to safely park. So now it is flipped around, and it is now able to comfortably park. All right. Yeah. And yeah, that concludes some of the cool stuff that we have been working on and are continuing to work on at Ati Motors in terms of trolley safety. Yeah, the floor is open for any questions that you may have.
Yes, so we have one more question. This is regarding the impact detection.
Right.
Does the IMU and current spikes suffice to distinguish actual impact versus minor bumps on the floor or perhaps slopes?
Yeah, that's a great question. We are filtering out a lot of that noise. So we are making sure that the spikes that we see are indeed true positives. So we are running some filtering on top of that. But you are right. I mean, these are the environmental challenges that we have. How do you differentiate between the trolley wheels getting stuck in a small crevice on the ground versus some 50 kg box falling between the vehicle and the trolley? So that's a great question. We do annotate maps in terms of features that you may come across like ramps. So you may be able to tweak your algorithm based on the knowledge that you are on a ramp. You can also infer that you're on a ramp using the IMU and gyroscope. We can infer that, hey, there's a bump coming ahead using a neural net. You can say, hey, I expect a bump to be there. Let us tweak the threshold for the current spikes accordingly. So there are a lot of techniques that we can use to get around some of these environmental challenges.
Okay. Uh, then and some kind of generic question that is saying what are the key steps for successfully implementing new safety solutions without disrupting daily operations?
Yeah, I think at some point you just have to rely on the data that you gather and make sure that you do your homework. So you can probably scout a place, do your homework about the trolleys, gather the data, perhaps simulate it on the Isaac Sim environment that we have, and then proceed to doing a deployment or an update at a site without being too intrusive.
Yeah. And one more question. What other components, no, what other factors complement technological safety advancements in Tugger environments? I could say that the operators and the floor personnel training would be one of the thing that would complement all our hard work. And yeah, up to you, Supratik.
Yeah,
That
I mean,
is
there are a
first
lot
thing.
of training, operational safety training that can be done. Of course, training on how to use the robot, how to interact with the trolley. There's a lot of other industrial standards that one can follow. I do recall visiting a site once where each of the lanes where the tuggers ply on are bounded by guardrails. So the humans walk on a pedestrian lane, which is guarded by these rails, and the tuggers are in a road, so to speak. So these sorts of small environmental changes, improvements rather, can go a long way. But of course, the robot always has to be accountable for its actions. So we will rely on our sensors and the safety
No,
to do that.
yeah, and then we have our FM giving us the warnings, errors, obstacle detection messages, etc.
Yeah,
A
yeah. So you instrument
person,
with other sensors to enhance the safety around pivotal intersections around the factory, and that'll give you an added layer of safety.
yeah, and then we have hooters which will be giving out some kind of a warning if it is undetected and the obstacle has not been
So
cleared more than 30
yeah, I keep
seconds.
saying that there is no problem that can't be solved by good UX. So yeah, you can have a lot of color indicators, HMIs,
Yeah, and
replays,
maybe
others.
one session on FM actually. Next time we could ask our engineers to talk about FM in the next webinar. They can
Absolutely.
choose that as a topic, which would actually give help many people to understand how do we get all these insights.
Yeah, that will be
Uh,
great.
yeah, and then we have one question from Sudipta. How do you detect slippery surfaces such as an oil spill in a
That's
shop floor environment?
That's a great question. So we have wheel encoders for the wheels, but you're right in saying that if the vehicle is trying to gain traction on a slippery surface or a snowy surface, the wheels may slip. So the vehicle itself may not be moving, but the wheels may be saying that they're moving, and therefore you have slip. You have wheel slip. You have an IMU and gyroscope on board the LiDAR, so that will tell you what the vehicle is doing. So you can pass it through something like a Kalman filter, and you can estimate that, hey, the estimates given by the odometry, which is the wheel encoders, and the estimates given by the IMU are diverging. And therefore, you can say that you are slipping, and you may want to slow down, try to get traction or ask a human operator for help.
Okay, and we will be closing in another 5 minutes. And I have one question. Hope this is the last question. Guys, please input your questions as soon as possible. We'll be closing this session in another 5 minutes. So we have a question asking what software available for material communicate with helper. So I'm
Um,
not
I'm assuming you're talking about something like an ERP system where you're tracking the material that we are tugging on the trolleys.
that
If, if,
is
if,
supposed to
if,
be,
if that is
yeah.
the case, then we do have plugins on our fleet manager that are basically you can plug into any ERP system and you can track the material that is being tugged. So perhaps that's something that we can cover in the next webinar series.
Yeah, as we said, we have some softwares where we mark the stations, pickup stations, material stations, which material, where to go, etc. All this, I think that should be covered with the Fleet Manager software webinar series.
Right.
So yeah. So since that is the last question, I think we can wrap it up now.
All right. Yeah, do feel free to reach out to either Shilpa or myself if you have any questions about some of these topics. And yeah, looking forward to seeing you guys in the next webinar. Thanks.
Thank you guys. Do write to us. Visit our website atimotors.com. Thank you very much. Thanks a lot, Supratim. You have covered a lot of challenges and how, as in Ati Motors, we have solved those challenges. Did we get any challenge today through the questions? Are we going to solve them for the future?
Nothing the engineering team can't solve.
Super. Okay, guys,
All right.
that's
Wish
a
you great
wrap
luck.
then. Yeah. Thank you very much, everybody.